workshop. Thanks for coming up so early. So we're happy to have Po-Ling from Madison, who's going to tell us about the robust regression.
Okay, thanks very much to Elias and the other organizers for the invitation. It's great to be back in Berkeley and at the Simons Institute. So I'm going to be talking about a project that I've been thinking about for a while. It's taken a while to write, not because it's difficult, but because I have a lot of other things that are on my mind. So for many years now, I've been working on problems related to high-dimensional linear regression. And this slide is just for some of the notation. So we will want to estimate the unknown parameter vector beta star from IID observations xi, yi, where xi and beta star are p-dimensional and yi is a scalar. And what we have is a situation where the number of dimensions is larger than the number of observations, and therefore we'll assume that there's some underlying structure, in this case sparsity of the unknown regression vector. Okay, so I'll cut very quickly to the idea of how we can encourage robustness. So what we use is just classical ideas from robust statistics, and the idea is that instead of trying to minimize sum of squared errors, if we want to deal with some kind of heavy-tailedness or contamination in our observation pairs, then we might instead want to minimize some other loss function applied to the data. So in this setting, L corresponds to the loss function, and this is just sort of a textbook picture of the difference between using ordinary least squares for regression in a two-dimensional setting versus some other loss function. So on the left side, you'll see different types of loss functions, including the usual quadratic loss in contrast to things like a Hoover loss, which is here in red. So that's quadratic and then becomes linear, and then other types of non-convex losses. And if you look at the behavior just on these data points in this picture, you can see that the least squares fit will sort of be halfway in between perhaps the true curve and the outliers, whereas some losses such as Hoover and this non-convex Tukey loss will tend to do better. Okay, so in classical robust statistics, there was a lot of focus on sort of minimax optimality or optimality from the point of view of asymptotic variance in the setting where n is going to infinity and p is fixed. But of course, in high dimensions, what might happen is you need to change what sort of objective function you're optimizing and add some other penalty to the term, and also analyze some slightly different quantities. Okay, so what we study here is a penalized version of a robust regression function. So this is robust because we're thinking about loss functions that are not just the squared error loss. However, we are assuming that yi and xi are still related via a linear model. And I should point out that in this linear model that I mentioned before, we're assuming still that all of our epsilons are IID from some distribution. So the theory does not carry over also to the case of adversarial contamination, although I really wish it did. Yeah, Elias, question?
So, are you only interested in solving this optimization problem over the samples, or you're also interested in what generalization characteristic it has?
We're just looking at estimation error. So we want to know how quickly the output converges to beta star in certain metrics. All right, so we're going to assume that the errors, so that the robustness aspect, the part that doesn't come from a standard Gaussian linear model, is that the epsilons might come from some kind of heavy-tailed distribution, or if you want, they might come from a mixture distribution where a 1 minus epsilon fraction is sort of the clean, nice data, and then the other epsilon fraction is from some other distribution. Okay. Right, so what we want to do is, in high dimensions, we want to analyze this particular objective function. So the questions that we might ask are, well, first of all, if we actually want to look at a non-convex loss function. So these types of non-convex loss functions in the literature are called redescending M-estimators. So the idea is that if you plot the derivative of this blue curve, then the derivative will descend down to 0. And this corresponds to this notion of a finite rejection point. So if you have points that are beyond some radius away from the true curve, then the impact that they have on your estimating equations is 0. Okay, so if we actually wanted to optimize one of these M-estimation problems where the loss function was non-convex, then even in low dimensions we would have a problem. a problem in the sense that we need to start to worry about, well, are there local optima, what do they look like, and do they also behave well? And of course, when we add an L1 penalty, that's not going to make things any more non-convex. So the same questions arise. So what can we do with the fact that there might be multiple local optima? And maybe another question is just, well, I gave some reasons for why one might use a non-convex loss function or something like a Huber loss in the classical setting. But in a high-dimensional setting, you might be looking at slightly different quantities and slightly different notions of how one loss is better than the other. So in this talk, I'm going to try to address these, both of these questions. So then another important part of this talk is this idea of scale calibration. So what does that mean and why is it important? Well, so if you go back to just the idea of why Huber said that the Huber loss was sort of the best type of loss to look at, then in classical robust statistics, there will be this notion of looking at minimax variance and minimax bias. And the sort of derivation that one can write down is that the Huber loss is minimax optimal when you look at the asymptotic distribution of the estimator when you look at contaminated data. All right? So if you are simply looking at data from a normal distribution, then what minimizes the asymptotic variance? That corresponds to maximum likelihood estimation. Okay? And so then you should look at some kind of a quadratic loss if you're doing location estimation. Why do you get a Huber loss, which is quadratic and then linear? That's because you don't just want to look at the best estimator when you are looking at data coming from a specific normal distribution. You want to look at a contaminated normal distribution. And what does contamination mean? Well, we heard a bit yesterday about Huber's epsilon contamination model, and that's exactly what this talks about. This is like a CDF that is within an epsilon neighborhood of the standard normal CDF. Right? So what you can do is you can actually write down what this maximum, sort of this worst case asymptotic variance would look like for the Huber estimator and compare it with all other M-estimators you could possibly write down. And what happens is that the best estimator, the best shape of an M-estimator, in fact, is the Huber loss. All right, but there are a couple of things that you need to be a bit careful about. So obviously, this is going to depend on epsilon, right? Because we're looking at some minimax, some worst case neighborhood around a normal distribution. If epsilon changes, then you can imagine that the shape of your Huber loss is going to have to change. Another problem, though, is that actually the derivation is also for a setting where you're looking at a contaminated standard normal distribution. And if you actually write down carefully what the shape of your Huber loss should look like, if you're looking at not a standard normal, then there's also some hidden dependence on sigma. Okay, so sort of this nice clean theory which motivates the Huber loss, and which is great because we've studied Huber loss in lots of other areas since then, and it's been great for various reasons. There are still some sort of hidden questions that one needs to deal with. And yeah, so this is also what I'm saying here, that well, you have a maximum likelihood estimator, and you need to be a bit more careful depending on exactly what distribution you're looking at contaminating from. Okay, so this previous slide, this is if you're just looking at a location family. So it's like you just want to use a more robust estimate than the mean. Then Huber's theory is for one-dimensional estimator and says that you should look at a Huber loss. In a regression setting, it gets even more complicated. Okay, so the problem is that when you're looking at a regression setting, we're trying to apply this loss function to the residuals. And the standard ordinary least squares regression says that you apply the loss function, you apply the squared loss just to the residuals. And then it turns out that the scale parameter doesn't matter. So if you can think about doing maximum likelihood for your regression parameter estimator when you have a linear model and when your data are coming from a standard normal distribution, not standard normal, from a normal distribution with zero mean and any variance, you'll still end up with the same maximum likelihood expression where there's no dependence on sigma, because the sigma will just come out as sigma squared. Okay. However, imagine a case when you are not looking at a Gaussian model. So you could think about a contaminated model, but that just sort of complicates things. So for now, just think about some sort of other model where, I don't know, maybe it's a t distribution. Or maybe it's a t distribution with a couple more degrees of freedom so that we have second moments. Okay, so you basically have some other distribution that is some shape that's not the Gaussian model. And you can imagine writing down what the maximum likelihood estimator will be. Okay, so the maximum likelihood estimator will correspond to another loss function, which is not the quadratic loss. and it will have a dependence on sigma that you can't just factor out. Okay, so now we have a slight problem because, well, if we want to figure out the beta that minimizes this objective function, then that's only half the story. So there are different proposals that people have given over the last couple of decades. And one that's kind of popular is what's called the M-estimator. So it's sort of saying, well, if someone actually told you what a good scale parameter was or what the actual scale parameter was, then it would be a simple problem. Okay, so even if I were using a loss that wasn't just the quadratic loss and was something that corresponded to some weirder MLE, I could just plug in some estimate of sigma star, and then I would be back in the M estimation problem again. So it's not like all the problems are gone. I mean, if I have a non-convex loss, I still need to optimize this thing. If I want to move to high dimensions, I still probably need to put a penalty on it and analyze it. Okay, but this slide is just to say that in linear regression, the unknown scale case is still kind of complicated. Okay. So as I said, there have been various proposals in the robust regression literature, and they all have some benefits and some shortcomings. So I think these authors here have shown that these estimators might have good breakdown properties, but then in terms of optimization and where the local optima lie, I think the theory is still very much incomplete. So I'm not saying that we have solved these problems. I'm just saying that my proposal that I'll show you for getting around the scale problem sort of addresses the issues that are not exactly addressed in these proposals. And just maybe to say a little bit more about what other people have proposed. So it all comes down to having some good estimate of the scale, at least this M-estimator. It's called an M-estimator because some of the proposals say, well, if I want to estimate the scale, let me use an M-estimator of scale to get that sigma. And of course, one can imagine that you don't have to actually get sigma star exactly. If you get some good approximation of it, then your beta hat should also be approximately good. But then the question again is how do I get a good estimate of sigma? Because remember, sigma is not the scale of your x's. It's not the scale of your y's. It's the scale of your epsilons. These are your residuals. And if you don't have a good estimate of the regression parameter, then how are you going to get a good estimate of the residuals? So some of the proposals that seem to work well in practice are to look at something like least median of squares. So least median of squares says maybe you can look at the beta that optimizes this optimization problem. So this is a little bit hard to parse, but this is a minimization only over beta. And what does it minimize? It minimizes the median of the residuals. Okay, so that's what this R means. And then the fact that I'm truncating it at n minus n delta means that I only want maybe the bottom 90%, so that things are more robust. Similar type of flavor is what's called least trim squares regression. So least trim squares regression has also been suggested as a way to just go ahead and solve the problem already without estimating sigma. And the idea is that instead of summing up the squared residuals, you sum up maybe the squares of the bottom 90% of the residuals, and you call that fit beta. So the MM part of it says, well, let's just use that to estimate beta, because we don't think that that will be the best estimate of beta star that we can get altogether. Let's use that as our estimate of beta hat, and then based on that, let's maybe take a median of the residuals that we get, and let's plug that in. So these are well-studied proposals, and as I said, they seem to work well. But the theory in particular, like, will this always find you a good local optimum if there are multiple local optima is kind of unknown. Okay. Yeah.
Also, computationally, they are difficult, right?
Yeah. Yeah, that's true. Yeah, so minimizing this is going to be a non-convex problem.
So squared as well,
right. So not only is it computationally difficult, but also all the types of analysis you might want to do to show statistical consistency that depend on convexity don't work. So yeah, very non-convex problem. Okay. Right. So here I say that these things will work if we have some reasonably good initial estimate of beta or sigma, but it's still kind of difficult. Okay, and then as I was sort of doing more background reading on what people have done, so there's some more sort of classical older papers where people were addressing the question, not in the regression setting, but again, just looking at location estimation for how do you actually choose this Huber parameter if you don't actually know what your sigma or your epsilon is. These sort of proposals exist, and they have some characteristics in common with what I'm going to describe, but not exactly. So essentially what they do is they say, well, let's choose different sigmas, and let's do sort of a grid of values. And how do we compare the quality of the estimates? Well, for every sigma, I get a location estimator, and I can use some sort of estimate of what the asymptotic variance should be. And I do that for everything in my grid. And if my goal is to minimize the asymptotic variance, then I compare all of those proposals and I take the minimum. But again, not exactly known. Well, the theory is somewhat incomplete here. So what I am going to talk about, I guess I'm not going to give you the scale calibration part yet, but let me tell you what one can do when you actually know the scale. So sort of the short story is that the proposal that I have is that we are also going to kind of compute the estimator for a grid of scales. But the way that we compare the estimators isn't going to be quite the method that I've just outlined. So given that my idea is to compare the estimator for a grid of scales, the question is, well, for a particular scale parameter, if we went back to this regression setting and we plugged in, I guess the regression setting is here, just imagine it's this with a penalty, right? So if we actually plug in a particular scale, then how does this behave? So this is a paper that I had a couple of years ago, and this paper was exactly this question. Actually, to be honest, when I was preparing this paper, I didn't quite realize how much it depended on scale, because the assumption goes, okay, well, there is this scale parameter that you are cooking into your loss function, right? And then if you put the right assumptions, and the right assumption had something to do with second moments of epsilon essentially being bounded by a constant multiple of the scale. But as you dig deeper into the classical robust statistics literature, you realize that that isn't exactly quite satisfying. Okay, so the type of result that came from this earlier paper was twofold. So for a while now, I've been interested in sort of the interplay between global and local optima in certain statistical types of problems. And the nice result is that one can show that both local and global optima of a certain type of non-convex loss function. In particular, the type of non-convex loss function that shows up in exactly these types of robust regression proposals have the property that both local and global optima are close to the true beta star. Okay? And I'm going to talk a bit more about exactly what these conditions mean. So let me flip back to an earlier picture. So what these conditions mean is that I still need some sort of curvature of the loss function. So the saving grace, if you look at this picture, and comparing the red curve and the blue curve to, for instance, the green curve, is that the green curve is an absolute value and that has no curvature at the origin. Whereas if you look at a Huber and a Tukey loss function, well, they get kind of weird if you go further away from the origin. So think about further away from the true beta star. But close to the origin, they're still kind of nice and they're more or less quadratic. Okay, so the conditions that I impose essentially say that you have some nice curvature of your loss function close to the origin. So this theory applies to cases like a Huber and Tukey loss. And this probably seems reasonable to those of you who work in high-dimensional statistics, because you know that you always need some kind of restricted eigenvalue type of condition, and it has to do with the curvature of the loss function. Okay, so basically that is what allows us to use this sort of analysis. On the other hand, if you use some kind of a non-convex Tukey loss, then you could imagine that since it becomes totally flat further out, there might be other local optima that are sort of further away. And this is something that you can see in simulations as well. And so the idea is that it's not true that all of your local optima are bunched around the global optimum, which actually does happen in other cases. But what we can guarantee is that certain local optima are well behaved. So certain local optima, meaning the ones that are sort of close to beta star, are actually also bunched together. Okay, so when you read this statement, it's not just saying that local optima that are already very close are very close. So you can think about R as sort of a constant radius region, and I'm saying that within this constant radius region that's sort of governed by the curvature of your Tukey or Huber loss, any local optimum in that region is actually very, very close to beta star. Okay, right, and so then the question is, where is this hidden requirement that your scale parameter is bounded. So essentially your scale parameter, well, here I didn't even have a sigma cooked into my L, but essentially it's saying that your curvature of your loss has to somehow respect the variance of the epsilons. Because you want to think about it as you're throwing down these data points and you have some kind of, let's say, a Huber loss in multi-dimensions, right? And you don't want your errors to be so far out that they're only on the place where the Huber loss is linear. So you sort of want to calibrate your width of the Huber loss, which here corresponds directly to this radius of your loss function with the scale of your epsilons. Okay. And then I guess the other thing to note is that, of course, if we care about local and global optima and actually finding the good ones, we also need to guarantee that we can actually find them. And the other component of this work was to say that, in fact, there is a way to provably find them. And as is common in a lot of the non-convex literature these days, it's the idea is that if you have a proper initialization, a clever initialization, then you can run some sort of first-order algorithm, for instance, that will find you a good enough local optimum. And so how would we do this? Well, so the recommendation is that we use something like a Huber loss at first. Okay, so the idea is, so here I've kind of written it out in all of its complexity. So originally I was interested in putting all sorts of non-convexity on my problems. So think about like a Tukey loss and a SCAD penalty or something like that. So if that's what you actually wanted to optimize, then what you should do instead is you should use some kind of a Huber loss with an L1 penalty first. Optimize that because it's nice and convex, find a solution, and then that provably will get you within this nice basin of attraction and find you a good local optimum. Okay. Okay, so before I move on to the next slide, so one other comment is, well, so when I came up with this method, I was excited, but then I also realized, well, I was sort of thinking, well, if the initialization already gives me a good point, then why do I run the second step, right? But of course, if you're more well-versed in statistics, you'll realize that, you know, it's not just about consistency, right? It's also about efficiency, about variance. And the whole way that I was motivating Huber loss to begin with was saying, look at the variance of these estimators. And when you start talking about variances, then you start thinking about things like maximum likelihood estimators. And when you think about a maximum likelihood estimator for a distribution that's not Gaussian, then you really should be using some kind of loss function that's not convex. Okay, so, and you can see also if you simulate this process and you just look at the variance of the first step only, then the variance of that estimator is going to be worse in general than the variance where you just run the second step. Okay, so before I get to the scale calibration part, I also want to say a couple more words about this. So I think the main step that sort of demystifies how the loss function can play off against bad heavy-tailed errors is the following. So if you want to analyze a lasso, then what you would normally do is you write down the basic inequality. So you say that you look at the, so lasso is just squared error loss and L1 penalty. And you say that if you evaluate this at beta hat and you compare it with beta star, then you can rearrange the terms and end up with some function of beta hat minus beta star. And then provided lambda is suitably chosen, then you get this sort of inequality. Okay. And then the question now is, so where exactly is the assumption that the epsilons are well behaved coming in? Because if for lasso there was no assumption on epsilons being Gaussian or anything, then who really cares about this, right? Okay, so as you'll know, if the way that we get these sorts of fast rates of convergence for the estimator that comes out of the lasso is we want to say, well, according to this theory, my optimal choice of lambda should be to choose lambda as the infinity norm of x transpose epsilon over n. And if my epsilons are sub-Gaussian and if my x's are sub-Gaussian, or maybe if I have a fixed design and my x's are well behaved, then with high probability this thing is bounded like square root log p over n, and so then everything is great because if I choose lambda correctly, then the bound is like square root k log p over n. Okay. So the nice thing is that if we now change the calculation a little bit, and instead of using a squared loss function, but we use a different loss function. So we go back to how we were going to begin with the basic inequality, and we write down an arbitrary sum of L of something, and we rearrange this inequality. We should also get some sort of a bound. And what happens is we end up with the same sort of result, but instead of looking at x times the vector epsilon over n and the infinity norm of that, the loss function, the derivative of the loss function is now wrapped around the vector epsilon. So it's L prime of epsilon 1 up to L prime of epsilon n. And so the nice thing is that now when we try to talk about the optimal choice of lambda, it no longer depends on what the tails of epsilon are. Because now we have this loss function. The loss function is counteracting whatever epsilon is doing. So if your loss function is something like a Huber loss, then your L prime is going to be bounded, right? L prime is like linear, constant, linear, constant. So no matter what your epsilon tails are, it's going to chop them off. And therefore, L prime of epsilon is going to be sub-Gaussian. And therefore, we can plug in a square root log p over n here. Okay. All right, so of course, and so technical challenges are, of course, I only showed part of the equation. So, I mean, one thing I did was I only showed you a small sketch of a proof for global optima. Another thing is that, as you know, a lot of the hard work in showing these high-dimensional results comes in analyzing things like a restricted eigenvalue condition. So it's not quite as simple as saying, well, write down the basic inequality and then get this inequality. There's something else in between where you need to look at the curvature of your loss function. And of course, now this is where we need to be a little bit more careful. So in the things like Tukey loss, right, we need to worry about actually having this curvature and actually having it. So that's where the epsilons can't be too spread out because we need the curvature to play well with the variance of the epsilons. Okay. Yeah, so technically speaking, well, in terms of technical conditions, this is addressed by the local curvature of the robust loss around the origin. Okay, so I think let me skip the details of this, and I'll just say that, well, so the very technical nuts and bolts of this were that instead of looking at a restricted eigenvalue condition, we had to look at what has now been known in the literature as restricted strong convexity, but then we had to limit this to some constant radius region because that's what's satisfied by these sorts of Tukey losses that are convex only in a small radius. Okay, so let me skip through that. Great. So now for the scale calibration. Okay, so for the scale calibration part, the idea was, it's actually very simple. So I thought about all sorts of other ways to get around this problem of scale estimation that had to do with joint estimation of beta and sigma, which you can do in certain cases, but not in quite the setting that in quite the generality I wanted. And so the idea was to use Lepski's method. Okay, so the slide is kind of busy, but as I said, the idea is calculate the estimator on a grid of values. Okay, so here I'm just sort of being a little bit more concrete on what exactly my estimator means. And all I've done is I've changed my estimator a tiny bit, but this shouldn't bother you too much. So I just added weights W and W. Other than that, it's exactly the same as before. It's just I want to do my robust regression, and I want to put a sigma on the bottom to rescale everything appropriately. And then I have my L1 penalty. Okay? And the reason for the weights is simply that I want to be very broad in my analysis. I want to be able to say that even if I have heavy tails in the x's, that's not a problem. So some of these proposals by Huber, for instance, for joint estimation of beta and sigma. So Huber had a slightly different proposal for a loss function that turned out to be jointly convex in beta and sigma. But the problem is that that's not going to work in the case where your x's also have contamination. Okay, so in order to deal with the case where the x's might also have contamination, you add some weights. Technically speaking, when you start to take derivatives of things and make them concentrate, you don't only have to deal with x, but you can deal with w times x. And this is a good thing because what does your w look like? Well, it is often, well, it was proposed in the literature before also as this sort of an estimator that basically says if you get too far away, then just pull it in. Okay, so it's saying I'm still looking at an M-estimator, but some kind of a weighted M-estimator where I want to also pull in my x's. Of course, this might also bother you because now we're getting further and further away from maximum likelihood estimation, right? Because like if I actually had heavy-tailed x's and heavy-tailed sigmas, I probably don't want to just arbitrarily pull things in. And that's also why it becomes then important, even more important than before perhaps, to talk about the efficiency, right? So even if we get a good initial estimate, how do we get behavior that's about as good as if we were actually solving the maximum likelihood problem? All right. So back to Lepski's method. So Lepski's method is a method for sort of adaptively, yeah, question?
What is the B?
What is B? B is going to be constant. So little b and big B are going to be constants. And the rates will, of course, depend on these B's. Yeah. But you can also think about these as just a way to get an initial point. So it's fine if it's kind of rough.
The big B is not a matrix.
Big B is a matrix. Yeah. Yeah, because X is a vector. Yeah.
So the big B is what matrix we defined previously?
Sorry, so big B is going to be a P by P matrix. Little b is going to be a scalar.
But you are going to design that matrix, or is something?
You can set it to be whatever you want. Yeah, it could be a diagonal matrix if you want. Yeah. Yeah, I guess if you wanted to make things truly optimal, if your x's sort of have an isotropic shape, you would probably want to scale things appropriately. But here again, we're not worried about efficiency for the time being. Okay, so what is Lepski's method? Well, Lepski's method, as I said, it has kind of gotten more attention recently because I guess it's important to be able to calibrate things these days. And there are many things to calibrate. And in my concluding slide, I'll mention other things that I would really like to calibrate but aren't quite as easily done. Okay, so the idea is that we want to compute the estimator on a grid of values. Okay, but we're not going to, well, the way that we're comparing these estimators is going to be pairwise comparisons. And at the end of the day, we're going to categorize the points into either a good or a bad set. And then we're going to look at the good set and take a minimum over that good set. Okay, so what does this look like? Well, so first I should also mention that how you can apply Lepski's method is that you apply this sort of method when there is a range of values for a particular parameter and you're trying to figure out the best value of that parameter. And what you know is that if the parameter is bigger than some magical value that you don't know, the estimator will behave well. However, if you get further and further away from the magical estimator, the quality of your estimate will get worse and worse in a way that you understand. And that's exactly what is happening here, because here, according to the preceding theory that I told you, if we actually choose the scale parameter, well, I guess I didn't exactly make it explicit, but you can imagine, you know, if the optimal thing to do is choose your scale parameter to be, or your parameter of your Huber loss to be exactly the right scale parameter. If you overshoot by a little bit, you'll lose in the rates of estimation error, right? So if you go all the way out, if your scale parameter goes to infinity, you're just doing least squares. Least squares is consistent. It's just that the rate of convergence of beta hat to beta star is suboptimal. Right? So what we do know is that for any choice of the scale parameter that's big enough, we get a guarantee for the estimation error. It just gets worse and worse as we get bigger and bigger. And that's exactly where we can use Lepski's method. So Lepski's method says, well, let me find some rough parameter bounds. And so what I'm proposing in this is, well, okay, we want to know what is some good estimate of epsilon I, the variance of that. We have no idea what epsilon I is. But we do know that if epsilon and the x's are independent, then we can look at the variance of y, and that should tell us some kind of upper bound in epsilon I. And the good news is that you only need a very rough range on what sigma star could be, because at the end you're going to look at some kind of a doubling or log scale, whatever. So you start with sigma min, you'll get twice of that and 4 times of that, et cetera, et cetera. Okay, so then the procedure says, well, for every candidate, sigma j, so let's imagine I'm trying to decide whether sigma j is in the good set or the bad set. Let me evaluate the estimator for everything to the right of it. And let me compare those two estimators. So what does that do? Well, first of all, it says that everything that's in blue will, with high probability, by union bound, be in the good set. Okay, because I know that, so by it being the good set, I mean that the difference between the two estimators is going to be twice of this radius, right? So I don't know what beta star is. If I knew what beta star was, I could just compare everything with beta star, but then I would know what beta star is, so there's nothing to do. So all I can do is I can compare pairwise estimators, and I know that if both of them are in the blue region anyway, then they should pass my test, because the difference between beta hat at one of them and at the other one should be less than or equal to twice of this radius, right? Okay, but you know, Lepski's method is designed for a setting when I actually have no idea how the estimators will behave in the white region. So they might be good, they might be bad. And the nice thing is that Lepski's, well, at the end of the day, what I'm going to do is I'm going to declare everything that passed the test good, and then I'm going to choose the minimum as my choice of sigma star. And if it so happened that I chose something that was less than sigma star, then the nice thing is that beta hat evaluated at this point is guaranteed to be very close to beta star. All right, so it's not necessarily guaranteeing that the solution I get by doing this screening and choosing the arg min is actually going to be close to sigma star, but it is telling me that the beta hat evaluated at that sigma is close to beta hat at sigma star. Why is that? Because at some point I was doing pairwise comparisons to the right, and if sigma j passed my test, that means I must have compared it with something awfully close to sigma star, and therefore beta hat at sigma star is going to be close to beta hat at sigma j. Okay, so that's the idea. So just to repeat, the method is simply compute on a grid of values, but then you have this extra screening method that tells you what is in my good set, what's in my bad set, and then take the min over all of these. Okay, so at the end of the day, you end up with a result. And for those of you who have used Lepski's method, this is not surprising. And the hard work in showing this is not to show that Lepski's method works, but to show the required inequality that will then allow you to apply Lepski's method. Okay, and so then of course, then there are a couple of comments. So I mean, I think there are various constants that are hiding things. So what am I hiding and what am I not hiding? So what I am hiding is that, of course, the estimation error bounds will depend on some kind of restricted eigenvalue condition. And why is this a problem potentially? Well, I mean, these sort of constants are all going to show up in the comparisons that I'm doing in Lepski's method. So if I'm telling you that this constant is hiding something about the restricted eigenvalue constant, which is a property of the design matrix, then I also need to worry about that when I'm actually using Lepski's method with this big C. My justification for that, at least for the time being, is that, well, I mean, I think assuming that you know something about the distribution of the design of the covariates is still somewhat weaker than knowing something about the distribution of the epsilons. Right? Because in theory, if you had a lot more data, you don't even need the pairs of xi, yi pairs, but if you have more observations of xi, maybe you could estimate something about the curvature or restricted eigenvalue parameters. I'm not saying this is realistic, but at least it's more realistic than being able to say, someone has told me something about the distribution of the epsilons. Okay, so this does not require any knowledge of the scale parameter of the epsilons. Another nice thing is that the way that we've set things up, so there's been a lot of work on tuning-free lasso type regression. Usually lambda depends on the scale of the epsilons, but we've set things up in such a way that it doesn't depend on that. So, so technically you don't actually have to tune lambda here. Okay, so now maybe let me just say a couple more words on efficiency. So this is something that I've sort of skirted around. And it's also an area where I think there is still much work to be done. I think nobody has really had the last word on efficiency in high-dimensional regression settings. But at least what I've done here to improve the efficiency of my estimate is to follow this literature also from classical robust statistics on how to improve the efficiency of M-estimation. And so Peter Bickel has this very nice paper that proposes, or I should say, well, there were others who also proposed this, but he analyzes rigorously the behavior of these so-called one-step M-estimators. And this was exactly for the setting when you might want to minimize some other M-estimator from the point of view of maximum likelihood estimation, but all you might do to begin with is to minimize some sort of convex function and start with an initial point. And the bottom line here is that, in fact, if you just do one step of what turns out to be Newton's method for minimizing the loss function that you really care about, then asymptotically the behavior of the single step estimate is the same as if you were actually to minimize the real maximum likelihood non-convex problem that you wanted to. And this is something that has been studied, that has drawn attention recently in ordinary least squares high-dimensional lasso estimation, because people were interested in doing inference and trying to construct confidence intervals. And so the nice thing is that there's already some mathematics in place for understanding and analyzing what these one-step estimators might look like. Okay, so basically what I proposed and what I derived some math for was to say that, in fact, if you do this sort of one-step estimator, then the asymptotic variance that you end up with is exactly what you would like to have. So maybe I should just explain this a little bit more. So if you study robust regression, robust M-estimation, and you're looking at the asymptotic variance of an estimator, then the sort of term that shows up is going to be, so if psi is your derivative of your loss function, the type of term that shows up as your asymptotic variance is exactly something like expectation of psi squared times your distribution over expectation of psi prime squared. And the nice thing is that if you now look at the best possible psi that minimizes this factor, then that corresponds to the negative log likelihood, which I think I wrote down somewhere. Yeah, so maybe I'll go back. So it turns out that the best possible psi that you could use here to minimize this term corresponds to the derivative of the negative log likelihood. Right? Because so here psi is my derivative of my loss function. So that's basically saying that if I do maximum likelihood estimation, so I use a negative log likelihood function, then to get the minimum asymptotic variance, I should be taking a derivative. Okay, so maybe I won't go into more detail here, but I should just say that where this is not exactly completely satisfying is that I mean, I think what we would like to do a lot of the time in high dimensional statistics is not just look at sort of the asymptotic limit, and what we would really like to do is perhaps look at the variance of an estimator as a function of n and k and p, and understand exactly what is the right loss function to be using in that setting. Okay, so maybe let me just wrap up with this slide in the conclusion. So, as I said, there are other things that would be great to be able to calibrate. I've thought about them a little bit. I don't really know exactly what to do yet. So one thing that I've thought about on and off is just this least trim squares objective function. I thought about it for a while because I thought, well, if someone can actually analyze what the optimum of this very ugly objective function looks like, say that that solution is quite close to beta star, and then try to recover a sigma from it, then that would solve all my scale parameter problems. Now I'm approaching this from a slightly different perspective, which is that somehow if you want to do least trim squares and you're looking at maybe an epsilon contamination model or something like that, then you would really like your trimming parameter to depend on something that you don't know ahead of time. Okay, so the idea is you have some kind of outlyingness, and I'm not quite sure what way, and maybe you could imagine something like using Lepski's method and choosing your trimming parameter, and the problem is that, well, first of all, we don't really have a guarantee, I think, on how well your estimator will behave, but also the way Lepski's method is designed, you want your error guarantee to depend in some way on the parameter that you're choosing, and it's not quite so clear here. And then another question that I mentioned earlier is just this idea of doing one-dimensional location estimation where you don't know sigma, you don't know epsilon. Now you have two things to play with. And as far as I know, nobody really knows what a proper variant of Lepski's method would be in multiple dimensions. And if one could solve that, then there would be lots and lots of great things that one could do, not just in this field, but also other problems as well. So yeah, let me just wrap up with that. So thanks for your attention. And this is almost on the archive. It will be early next week. Questions? Sheila.
So you focus throughout on estimation error. So what happens if you do prediction error, and is there like an easy way to fix something like cross-validation than to pick your scale parameter?
I haven't thought about prediction error. I haven't seen classical robust statistics work on prediction error, but I could be wrong there.
Is there a good reason?
Not that I know off the top of my head. Yeah, maybe asking one of the experts here at Berkeley would be a good idea.
I've got a question. So in your previous slide, you said something about the optimal Huber parameter.
Yeah.
Which is, isn't that parameter like the C parameter or whatever, wherever you start to switch to the linear loss?
Yeah, yeah.
And isn't that sort of related to the scale of your errors as well? So
yeah, so that's what I'm saying. So if we step away from regression and we start to think about the optimal Huber parameter for the point of view of just using an M-estimator for location estimation, then the nice theory in the classical statistics books will tell you that exactly what that optimal parameter should be as a function of epsilon, assuming that the scale is 1, assuming that you're contaminating a standard normal. And if you try to solve the problem instead where you have, you don't know epsilon, and for different epsilon and a different scale, then your Huber parameter will depend on both of those. So then the question is, yeah, so somehow you have to come up with some adaptive way that would deal with both of them.
Yeah. You said early on that you kind of wish this would also be good for adversarial contamination. Are there any assumptions we can make, if the adversary isn't arbitrary, but that you think this analysis could extend to?
No, I mean, currently everything depends a lot on things being IID. I mean, I've thought a bit about trying to prove something about Huber loss in the case of adversaries that can choose the points. I have some bound, but I'm not perfectly happy with it. So, I mean, my belief is that Huber is probably a good thing to do also in adversarial contamination, but I don't know of anyone who can rigorously prove that right now. Except maybe Ilias.
No, I have a follow-up question. So, I mean, the M-estimator is just a definition, right? Some optimization problem, but if you solve, you're good. Like, do we even know that in the standard Huber contamination model, this is going to give you a regression vector, which is going to be close, like, to the true one?
In adversarial case.
even in Huber's contamination model. So
yeah, in that setting it should be fine, yeah.
I actually don't think it's true. I think there is a root D in there.
No, I think in her model, if you only have errors, it's fine. If you only have epsilons that are Huber controlled, I mean, her x's and y's are not touched. I mean, her y's are, but if the x's are random, this is what.
Oh, if you don't corrupt the x's, I will leave it. If you, but in the.
But that's her model.
Yeah. Okay.
Yeah.
I have one more. So, just you sort of use efficiency as a benchmark in as something in high dimensions.
Is that the right thing to look at? Yeah.
I mean, you can't achieve it in some sense, right? Like unless you look at single coefficients or small.
Yeah, exactly. Yeah, that's where this J was hiding out. Yeah.
And so, what is the right notion?
Yeah, this I don't know. I mean, I started studying, or I derived these results on efficiency, which were based on what a lot of other people had done, right? Simply because I wanted to understand for myself, can I justify the reason for using Tukey loss instead of Huber loss? So that at least sort of justifies it, right? Or like, how can I deal with the fact that I just tacked some arbitrary weights on things and now my solution might have really high variance? But yeah, that I also don't think anyone has an answer to that.
Yeah. So you hinted earlier on when you use the two-step procedure, the second step would improve efficiency. So can you elaborate on that when you want a non-contact?
So that was something that that was from my earlier paper, which I guess now that there's this Lepski's method thing, I don't know that it would be necessary to do that second step. But at least that was also an attempt at dealing with the efficiency, and there my crutch there was sparsity. So it's like if we have sparsity in a beta min condition, then everything's just in k dimensions anyway. So then you can look at the variance in k dimensions.
All right, so let's take other questions offline and thank the speaker again.